Okay, so you did this warm up. What did you get for your dissociation equation? Oh, this marker doesn't work. I'm running out of markers very quickly here. What did you get for your dissociation equation for KCl? Who would like to take a stab at this one? I'm hoping all of you could do at least one. Well, not all, there's more than 8 kids, but who would like? Katie, go ahead.
K plus Cl minus.
So you mean K plus?
Yeah,
Plus?
yeah.
Cl minus. States?
Aqueous.
And?
Aqueous.
Have you remembered your charges? Have you remembered your states?
Yeah.
Very good. Okay, next one. Who would like to have a go?
Ca2 plus aqueous plus 2Cl minus aqueous.
Good. Somebody from the back. Sabrina.
Pb2 plus aqueous plus SO4 2 minus aqueous.
Good. This one, solid. Tatum.
2Al3 plus aqueous plus 3O2 minus aqueous.
Good. Can somebody just check this for me? Can somebody just check that that is soluble? Remember? Remember how we're supposed to do that?
We don't have oxygen.
You don't have oxygen?
No.
Okay, it is soluble. It is, I think. I have to actually look at it, but I think it is. Okay, this one. Oh, you don't have oxygen.
No.
Ah, darn it. Okay, so this one is not soluble. So therefore, what Zoe?
The different arrows, right?
We do those different arrows. Those are called equilibrium arrows because it exists that way and that way. So we do those fancy equilibrium arrows, and then our products are same as before, or same as you would predict. Brennan?
2Na plus O2
States?
aqueous.
O2 minus,
Yeah.
aqueous, aqueous. Hands up if you've got 1 to 2 to 1 ratio. Remember those invisible ones, right? So an invisible 1 to a 2 to invisible 1 ratio. Okay, good? What?
Wouldn't the number 3 have to have those arrows too?
When that number 3, yeah, check that for me. Is it insoluble?
Yeah.
So, good. Check your calcium chloride, or your copper chloride for me. Because that would be one that you, or that's calcium chloride, is it?
Soluble.
Soluble. And while you're in the chloride compound, you can check your other one, the first one, potassium. Soluble. Yes? Okay, so we have those equilibrium arrows if it's insoluble, and we have a straight arrow if it's soluble, because if it's a straight arrow, hey, as soon as I sprinkle, I'm getting a lot of ions, right? And with the equilibrium arrow, as soon as I sprinkle, it's like, ew, I don't really want to be an ion, I really would like to be a solid, and you get more crystallization happening than you do dissolving. Everybody understand? So on those equilibrium arrows, this way is dissolving, and this way is crystallizing. Right? Yes?
Are we going to be looking at the crystals we made?
Yes, thanks for the reminder. Can you remind me at the end of class too? Okay. Okay, let's finish this. HCl. Crystals are different than crystallizing, though, right? I mean, I know I jogged your memory, but we understand they're different. Crystals are hydrated salts. Crystallizing, I'm talking about the beaker of water. There's the saturated solution, and these ions are coming together and becoming a solid, whilst this solid is also decomposing into those ions. This is the dissolving bit, that's the crystallizing bit. Not that I can write crystallizing and dissolving on there, so I'm just going to put a big D and a big C. And so when I write NaCl solid, dissolves into Na pluses and Cl minuses, aqueous, it's also crystallizing into this solid again. This crystallizing is that. Those in the fume cupboard are crystals. Different. Okay? Okay. Okay, so what did you put for HCl, somebody?
H positive aqueous plus Cl minus aqueous.
Everybody agree? Starts as a gas, by the way. I didn't put that in. This starts as aqueous. This starts as aqueous. I wouldn't expect you to know that. I would have put that in if it was a test or something, okay? This one, H2SO4.
2H plus. Aqueous.
And?
Plus SO4, 2 minus aqueous.
Okay. And ethanoic acid. I gave you the name because I wanted you to realize it was an acid. What makes an acid an acid? The H pluses. So how do I get an H plus off of that? It's either going to come from here or here. Does anybody know where it comes from? The last one. Because this CH3COO minus is actually a polyatomic ion in your data booklet on the polyatomic ion table. It's called ethanoate. So you can actually find it. Okay? Aqueous and H plus aqueous. Everybody okay? Any comments? Okay, so here's now today's lesson, and we're going to bridge off of this, okay? So, you know in Science 10, where you did, what's in the nucleus, and what's in the outer shells? Yeah? And you could tell me how many protons and neutrons were in the nucleus of sodium, and right? Let's talk about hydrogen for a second. Just the hydrogen atom, not H2, just H by itself, the hydrogen neutral. How many protons in hydrogen?
1.
1 because its atomic number is 1. How many neutrons in hydrogen? How many neutrons in hydrogen? How do you figure out neutrons? Pardon? There are none. You do the maths minus the number. So you have 1.01 minus 1 is 0. So there's 0 neutrons. And how many electrons in the atom of hydrogen on the outer shell? 1 electron. So a dot and cross diagram would look like that. Right? Everybody okay with that? When H becomes H plus, looking for my other marker. Anybody see a red marker somewhere? There, that one. Ooh, and a blue one. Ooh, Christmas. When it becomes H plus, how does it become H plus? So back to our unit 1, because our midterm is coming up. H with the outermost electron. How does it become H plus? It must have lost an electron, right? So I'm going to erase this electron because now I'm drawing H plus. There it goes, it's gone. What is H plus then? What's left? Are there any electrons left? Are there any neutrons left? What's only left?
Proton.
Proton. So what is H plus? It is a proton. It is a proton. That's it. By itself. A proton. Okay? So this HCl is a proton and Cl minus. This is 2 protons and the sulfate ion. This is a proton and ethanoate ion. See that? How stable do you think a proton, a positively charged particle, is going to be? Not stable at all. There's a whole lot of electrons around that it's going to be attracted to. Everybody get that concept? Okay, so this simplified understanding that came from Science 10, and did you write this down? Did you write that H plus is just a proton? Pen's frantically going right now. H plus is just a proton. So that proton's going to be very unstable, and it doesn't just exist by itself. This is really a simplified understanding that comes from Science 10, because we just want you to not have to think too hard, because you're just simply putting together
Junior clock change.
two different things to make a compound. Okay? So, I want us to look at how, I'm going to actually look at that one second, so I'm not going to rub it out totally. I want us to look at, if this is how we talked about it in Science 10, this is how we're going to talk about it in Chem 20. This HCl is a gas. It doesn't act like an acid at all. It doesn't neutralize the base. It doesn't turn litmus paper color. It does nothing that you would consider it to be acidic until I get it wet. If I were to wetten that litmus paper, right, like dampen it, and then wave it about in the gas, now my litmus paper will change to red. Huh. If I take an aqueous solution of a base and I bubble my gas through, now it'll neutralize it. If I take this gas and put it in water and then mix it with a base, it'll neutralize it. But the water has to be present. Okay? So Arrhenius, I'm going to talk about him later on, but I'm going to mention him now. So Arrhenius is a scientist in Science 10 who said, hey, acids have H plus in it. Bases have OH minus in it. That's Arrhenius's definition. Okay? And then some other important guys came around called Bronsted-Lowry and went, do you know what? There's some examples where you would have H plus, but it doesn't act acidic. And there are some bases that don't have OH minus. What's going on with these exceptions? So they looked at these exceptions and they discovered that, hey, H is just a proton. It can't just exist by itself. It has to exist in water. So it must be something about the water that makes it acidic. It must be something about water that makes it basic, because these things aren't acids and bases without the water, but they are with the water. Okay? So we started to kind of say, if we had HCl and we were reacting that and it needs the water, and what I'm going to do with this water, at first I'm going to just write it like this. Okay? And you know from the dot and cross diagram that there are two things here on this oxygen that are making it V-shaped. What are they?
Lone pairs.
Lone pairs, well remembered. So I've got a lone pair here and a lone pair here. What are lone pairs? Electrons. What charge are electrons? And what did we have a free thing flowing around? A positive proton. That positive proton sees these electrons and goes, I'm not hanging out by myself. I'm going to piggyback a ride with them. So actually, this proton here transfers itself onto there. And it's a shared pair of electrons. See how it's going to be a shared pair of electrons? But not one from you and one for me. Actually, the oxygen is bringing both to the table, and the hydrogen is just hanging out, eating all the donuts. Okay? So, what does it look like when it's done? Well, the Cl minus is all by itself, still, aqueous, because we've got all this water present. Everybody okay with that? Cl minus by himself? And the Cl minus is happy to be by himself because it's got a full valence shell, it's negatively charged, totally happy. Remember, this is an ionization. These three were ionizations in your warm-up. Those were dissociations over there, right? Dissociation ions, ionic compounds, and ionization is where we create the ions. So we had to create the ion, that shared pair of electrons got ripped over to the chloride because it's got a higher electronegativity, leaving the H all alone, just a proton, no electrons. Remember this? So that H is going to piggyback a ride onto those electrons. So here we go. Let's draw the water again. And yeah, I'm so glad those of you that are drawing this along with me. If you haven't already started, don't start now because you'll miss the point. And the H plus sits there like that. Shared pair of electrons. Its orbit is full, it's happy, right? 2 in the outer shell. And everybody else is happy, full shell. So this molecule here I can't draw it like this every time. Okay? So we write that like this. How many hydrogens do you see?
3.
How many oxygens do you see?
1.
Overall, what charge is that molecule?
Positive.
Positive. And this has a special name called hydronium ion. So what's hydronium ion? It's the H plus that you've known all along from Science 10, piggybacking a ride onto that oxygen. Why? Because H is not stable. It's just a proton. It's a free proton. Like nuclear reactions, free proton. Okay? And actually in physics, every time they talk about a proton being released, it's a hydrogen. Hydrogen, proton, same thing. So Bronsted-Lowry, which we'll talk about when we get it more into acids, started saying, hey, do you know what? Acids are proton donors. See how that's given away, it's donated a proton? So they started looking at acids and bases, and we will too at the end of this unit, in terms of proton donors and proton acceptors. Not H plus havers and OH minus havers. That was a really good starting point. Arrhenius gave us a very good platform, and then we had to look at the exceptions. And when we had the exceptions, we then had to kind of change our definition to be a proton donor or proton acceptor. So here, HCl is a proton donor. And that's why it's an acid, not because it has H plus in it. Okay, so donates the proton, la 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 la. Everybody okay with that? So we're going to do the same thing. I want you to write the same reaction. I want you to try it on your own for ethanoic acid now. So new example, different jazz. You need to now include your water in your ionization, not just like a dissociation equation. Okay, have a go. I'll put the answer on the board in 30 seconds. Check your answer with mine. You don't have to draw the water molecule, but if I were to ask you to explain why hydrogen doesn't exist as H+, or explain how the hydronium ion forms, that picture in your head helps you either write the words, or for me, you can always draw pictures and just kind of annotate what you're saying. Like, this is this, it goes here, this is this, it has these are the lone pairs. You can always do that for me, right? Unless I ask you to write an essay, you're having it in terms of like your lab report conclusion or something, then I need it to be sentence form. But explain on an exam, I'm happy with the diagram. So this, as long as I just sort of put, the HCl donates the protons to the lone pairs, and this is and forms this, and forms this. You're done. So that picture helps, but you don't have to do it. No, you can do it this way. This is the symbol way. I'm not explaining. I'm just giving. Hands up if you got this. Whether you drew the H2O or not, it doesn't matter. Hands up if you got it. Good. Well done. Okay, so that done now. That's how much solutions unit is going to be on your midterm. Okay, up till that, done. Learn all that for your midterm. So you're going to practice some of those questions.